Picture a ring of light looping around a black hole, so perfectly circular that it feels like a cosmic fingerprint. It's not a veil or a surface you could touch. It's a map of how extreme gravity bends every photon that dares to skim the edge of no return. Now push that scene into the chaos of two black holes spiraling toward a union. The spacetime trembles, horizons ripple, and gravitational waves shake the stage. In that roar, can a photon ring survive long enough to be seen at all? The naive instinct says no. Change is happening faster than light can respond, and any delicate orbit threaded near the photon region should tear itself apart. Yet streaks of light in simulations and the glow that survives the final plunge hint at something surprising. A ring that seems stubbornly stable for a moment, a fleeting halo that refuses to surrender to chaos. What is this stability if it exists at all? Is it a real persistence of geometry? Or a trick of our eyes trying to decode a dance governed by general relativity's most extreme rules? To understand why people ask this, we need to go back to the ground zero of photon rings. In a non-rotating black hole, light can skim a circular path at a radius of 3 times the mass, a photon sphere, where the gravitational pull is just strong enough to bend a path into a loop. In a rotating Kerr black hole, the situation splits. Prograde light moving with the spin can orbit closer and faster. Retrograde light is pushed outward. The image you'd see is not a simple circle, but a bright ring built from photons that whispered near these unstable orbits, each lurching through dozens or hundreds of circuits before escaping toward you or plunging in. The photon ring is not the event horizon itself. It is a horizon-shaking consequence of space-time geometry, a sharp edge carved by the most extreme bending of light. In recent decades, numerical relativity and ray tracing clarified that a sequence of ever narrower rings should appear, nested inside one another as photons loop times and times again. When the Event Horizon Telescope captured M87, that glow carried the imprint of those photon paths, a real, observable signature of a black hole's gravitational lensing in the wild. But that image was formed by a stationary, or slowly evolving geometry. The moment you introduce two orbiting masses, the story changes. The background is no longer a fixed stage. It is a dynamic, churning landscape in which the rules morph as the merge proceeds. The core mechanism, the deep dive, is a fusion of geometry, timing, and light. A photon ring forms because certain light paths cling to a critical set of unstable null geodesics. In a Kerr spacetime, those paths depend on the spin, orientation, and the observer's position. The light that ends up on the ring has skirted the brink of fate. It has nearly chased the photon sphere, executing one or more half-turns around the black hole before slipping away toward us. Now imagine two black holes spiraling inward. The gravitational field is no longer a smooth, stationary bowl. It becomes a rapidly shifting trampoline. The effective potential that guides photons is time-dependent and asymmetric. A photon that would have dared to orbit in a static spacetime may find the path altered as the masses approach. The horizons distort, and tidal effects reweave the photon's possible routes. In that moment, the ring's stability is not the same as in a steady Kerr hole. Yet the story does not end in collapse. There are two crucial elements that can conspire to preserve a ring-like feature, even in chaos. First, consider the ring-down phase. After the merger, the merged black hole settles toward a final Kerr geometry, radiating away asymmetries in gravitational waves. During this brief cadence, the space-time approaches a quasi-stationary form quickly enough that photons can complete several loops before the geometry changes too much. Think of a spinning toy top that's wobbling but still traces a near-perfect circle for a few spins before the wobble dampens. If enough photons are supplied from behind the camera's line of sight, and if their paths graze the dynamic region near the merged mass, a coherent, bright circular feature can re-emerge. The second element is the infinite procession of near-critical paths. Even when conditions are changing, there remains a family of trajectories that linger around the evolving potential long enough to contribute to a time-averaged ring. The photons don't stay in a single orbit forever, but a cascade of nearly bound paths can synchronize in a way that the image plane reads as a ring for a finite interval. In computer experiments, this appears as a moment when the image's bright ring almost snapshots a circular form and then slowly morphs as the final geometry settles. The story of discovery around this phenomenon is as much about numerical imagination as it is about physics. Researchers build dynamic spacetimes with full numerical relativity, then shoot virtual light through them with ray tracing. They track billions of photon paths backward from an imagined observer and watch which ones contribute to bright arcs. The signatures of photon rings emerge as caustics in the lens map, and their persistence is a diagnostic of how rapidly the geometry changes. In mergers, the brightest, most persistent ring correlates with the final black hole's spin and mass, a kind of gravitational fingerprint that survives the storm. The punchline is that even in violent, time-dependent gravity, pockets of stable-looking optical structure can survive long enough to be informative. The impossible stability is thus not a contradiction in GR. It is the dance of a ring that is allowed to exist briefly because space-time, for a moment, looks almost Kerr again, and because light can thread the evolving geometry with enough regularity to leave a trace. Why does this matter beyond pretty images? Because photon rings are grist for testing gravity in the strong field regime. They are direct probes of the space-time geometry near horizons, sensitive to spin, to higher-order corrections, and to departures from the no-hair theorem. If we can observe time-resolved rings during a merger, we gain a new kind of measurement, an optical gravitational waveform, if you will, that complements gravitational waves and tells us how space-time itself behaves when it's most dynamic. This informs us about the stability of space-time around compact objects, the reliability of the Kerr paradigm in real astrophysical events, and the interplay between light and gravity under extreme conditions. It also sharpens our expectations for the next generation of very long baseline interferometers, which might resolve these transient rings with enough cadence to watch the ring come and go, not just its shadow on a single frame. The conclusion ties the journey together in a single thread. The photon ring is a litmus test for how light choreographs itself in curved space-time, and merging black holes give us a brutal, beautiful stage on which that choreography plays out. The idea that a ring could endure amid the tremors of a space-time duet is not a contradiction. It is a reminder that stability, in gravity's grand theater, often means a moment of balance within a much larger, accelerating story. The ring's glow tells us where gravity is strongest, how fast space-time can rearrange itself, and how patiently light will wait for a doorway through chaos. If you want to follow the next act, where observations catch these fleeting halos in real time and physics pushes its predictive edge, make sure you subscribe.